Okay, welcome to the practical part of lecture 9. Now in this part we will basically re-implement or implement the linear model that we've seen in the lecture. Without further ado, let's get started. The first things we need to import are a couple of libraries or packages from Python. So the first thing is Seaborn. Seaborn will help us to visualize the realizations of the linear model later. Seaborn has much more capabilities than that. You can even create the linear model in Seaborn and then plot it. NumPy will help us with any vector and matrix multiplications. NumPy is a way to do vector matrix multiplications and many more fast. Then we have Pandas, which is another data science framework, which works on the basis of data frames, which are basically tables, and it can do efficient calculations on top of those tables. We have SciPy for other statistical computing, and matplotlib as another library for plotting. So Seaborn is based on matplotlib. So some of the functions that we get from Seaborn we can modify with matplotlib. And if we do that, then we have to quickly select our environment, which is Python 10 in this case, and we can import these packages. It takes a bit of time because Python packages are large, and then we can get started. So now the first thing we want to do is we want to use SciPy to do some statistical realizations. So in this case, we want to have 100 different randomly initialized points. Okay, so we just have a normal distribution, and from that we draw 100 IID points, and we can show these points here, and they're random, of course. So here we have the first 20 elements of that, but those are of course 100 elements in total, but that's a bit big, so we just show the first 20. Okay, and then now we have those random points in one dimension, and we want to get a linear relationship in another dimension. So what we do is, and this is something pretty cool with SciPy. SciPy gives you an array, and that array can be used to compute certain things with NumPy, for example. So we say y, those are the points in relation to that, are 2.5 shifted from the intercept, and then they have a slope of 0.75 times whatever realization x had. And then we also add some noise to that. So it's not the clear linear relationship, but I'll show later what that means. So we have this relationship and some noise, and then we can group the points in the pandas data frame. And this data frame, this data frame is basically this table that I talked about, and we can plot this relationship and show it in the plot. So actually, let's do the following. No, we don't want to use Markdown. We want to use code. Let's show the data frame that we have, and we call that data, and of course, not data frame. So let's show the data frame we have here, and that's exactly this sort of table that we have, which has different rows and then x and y values in that table. And I told you that there is some noise. As you can see, here is some relationship, some slope going up, but there's also a lot of noise. If we would remove that noise, what would happen is we would get a perfect relationship between the points, and that's exactly the line that we want to have. But of course, that's very easy to analytically solve. So to make it a bit more challenging, we added that noise, and that's also what we would encounter in real data. There is some noise, some measurement noise or something like that. Okay, and now we have this relationship. We want to find what is the model. So we don't know the distribution, we just come up with this, but this is a measurement, so we don't know what is the distribution. We just can do this by observation. And one way we've seen in the lecture is to define the residuals, which are the offsets from the points to a line, to find the best line that fits the points. So we have these residuals, and then we have the formulation of line, which is some parameters w and the x plus some offset w0. And in NumPy, it's very easy to calculate, in Pandas, it's very easy to calculate the means, the sample means of these drawn samples. We can just call data.mean. And this will give us for each column the mean value. There's other functions. We can also say we want the median, okay? And then we get the median. There's also standard deviation, and we can get the standard deviation. So this is very flexible and cool, because now with one command, we can find what are the means for each of these things. And then we basically apply what we've seen in lecture 9. So we subtract the sample means of x from each of the data points in x. We multiply that by the subtraction of the data points in y minus the sample means in y. We sum that up and divide that by the square of the sample means of x minus each point of x. And this will give us actually the slope. And the intercept can then be calculated by the sample means and the slope. And if we run that, you will see that the intercept is 2.63 and the slope is 6.693, which is almost the same as we have defined before here. It's a bit off. And why is that a bit off? Because of course we have added some noise. If we would do this here, remove the noise, and then again, it looks very much like a strong dependency. And we run this again, we would get the exact slope and sample mean. So the more noise, the more off this is. And you can also calculate by how much off this is. But for example, we can scale the noise a bit less. So let's say we have this distribution, but let's say it's only 25% of the noise we've added before. And still you will see there is some noise, but this relationship is much clearer, much more obvious than before. And now our model also gets more accurate. And we can see that now the offset is only by 0.04 or 0.03, while before we had a significant offset. So this is a fair implementation, but we can also see how that works in sklearn. They have implemented a linear regression model, probably a bit more efficient than we do. So we can import the linear model from sklearn, and then you can see that here the type of the data is a panda series, and again we can print the values of that series. Again, the whole thing is a data frame, and now we can apply this linear model that we define by calling linear model.linear regression, which is a class that we infer an object from, and then we can fit this model to the data, and we get this progress. And then once this is fit, the larger the data set, the longer it will take here, obviously, we can show the coefficient and the intercept. So here we have 0.747 and 2.53 or 2.54. And if we compare that to our results, that's almost exactly the same. We just have less rounding. We have head-to-head rounding here. So this model does the same as we did, but in a more general framework, and you can use it more generally. Okay, and then if we have unknown data, we can also run prediction. So if you have new data and you want to predict what is the y given x, so for example, again, this distribution shows, given someone's body weight, how healthy are they? Now we have a new person with a new body weight. We can ask how healthy that person is. And if we give a 0, we expect to get the slope. And that's exactly what, not the slope, sorry, the intercept. That's exactly what we get here. And we can do this for all the points. And then we can predict what the line looks like. So let's predict the points values given the data x. We can do this for all of the points, and we can store it in another column called predicted, and this will be our line. So, okay, give predicted, and then if we plot it, we can plot our line in that, and it looks exactly the relationship we wanted to catch. So given some x, this is the y that we would expect, and this is the y that gives the least errors or residuals according to the distribution that we observe. There's all of this can also be done in one plot, in one line. So Seaborn uses sklearn to do the line and then plot the data points as well. So if we run that, and maybe we have to say plot.show, then we can see exactly this. So it will calculate the line given the sample means. It will plot the points, it will plot the line, and even give some residual errors to the edges, which are a bit higher. And that's about it. That's linear regression in Python. And yeah, thank you so much for listening.